Finally Friday arrived here again. Repeat every week. Friday and Friday, Friday. Okay, let's continue. You will get the email from Higyu this morning for a probability model, which I really described quite detailed. And that's we're going to cover next week. In addition, I assigned some problem set, and as you notice, this semester I completely changed the type of the problem set. Rather than assigning an answer to this question for this particular number and get me the particular another set of the number, I feel this is time to change. So I give you total freedom. Hey, you generate the data set, you manipulate, then using the probability model, which I gave you, you don't have to limit yourself to 6 sets, which I really go through. Then I said this is bi-weekly project, which means you have 2 weeks. Then submit before the end of September. So then I really like to see you have some time to think about it. Keep thinking rather than busy to manipulate the number. Keep think and digest yourself rather than copy the things from the paper. Of course you may use a paper, you may copy the paper with understanding. Do with understanding. That's the clue for this semesters, okay? To generate the innovative idea, get the result based on your thought. So everybody could have a different probability model. Then you will see within a week or 2 why I'm insisting the understanding and use of the probability model. Because structural reliability is the falling into the category of the defining process of the model, probability model, then integration of the probability model, and that's the category it falls into it to compute the reliability index or reliability whatsoever. Okay, smile. Friday morning you should smile. See Arlene smiling. Good for you. Okay, we learned a few personality of probability model. The first one was the mean. To see the behavior of the model. And the mean value or expected value was the second one. Is the variance or standard deviation. What's good for the variance? What kind of the personality we discussed? When you go out date with the Yochin and Namchin, if they have high variance, is it good? Not very good. Not reliable. So that's a measure of what? Variance is a measure of? Yes, so dispersion. Okay. And what's a 2 property that's really good for normal distribution. That's the parameters you need. What's the third parameter? Jinggyun. What's the third parameter? COV? Okay, COV we defined in two different processes. So I mentioned the last Wednesday, be careful. Coefficient of variations, right? So, which is really normalized standard deviations. And what was the definition for coefficient of variation? Youngyan? Who cares? You will care until end of the semester. That's a sigma x over mu x, standard deviation over the mean of random variable, of course, which is nothing but normalized dispersion of the probability model. It standardizes it to make it the non-dimensional. That's what you did. And another COV is, what was it? The last Wednesday popped up. Hyungso, what was it? It's another COV. Another COV is covariance. I clearly spell out whenever I use the COV. Covariance. What's a covariance? Well, of course, we'll discuss that today too. Okay, two variables come into picture. And last Wednesday, I introduced another parameter, which is called skewness. And we defined the skewness, but we haven't defined the kurtosis yet. And this is all parameters to look at the behavior of the probability model beforehand. Personality of the person, I want to really find out. Whenever we interview the new faculty member, I go through the professional vitae, simply resume, and some resume, by looking at it, is very difficult to really understand his capabilities and the potentials and all that. So just using the mean is very difficult to define the probability model. So as a major, sometimes you need to really investigate all those parameters. That's what we are doing. So kurtosis, skewness is a measure of, what was the skewness? What does it do by looking at it? You feel this course is so easy, I don't have to study, right? It's easy, but you've got to really prepare and review. That's all you need. Full understanding. That's what I'm insisting. Otherwise, you can't use it later. So skewness is definition wise, what is it? Expected value of, like x minus mu x simply cube, right? And you can normalize it, dividing by sigma x cube. Just people happen to use sigma x cube to normalize it, but you don't have to. But at least the basic definition is this. If this guy gets you the negative, what does it mean? If this is a negative, what does it mean? It's skewed to the left. And if it's a no skew, then what happens? No skew, like a normal distribution, this is equal to 0. If it's a positive value, well, this is positive. If it's, like this is minus. It's a major behavior. We want to see the behavior. All you have to do is compute the skewness. Then especially when you have experimental data or analysis data, and beforehand, before you do any further, you might have to develop the probability model. Then to do that, then it's good to compute the skewness, kurtosis, and all that, to really see before I really use it for your research problem, to solve the research problems and vice versa. And or you can divide by this subscript x, as you know, that's the random variable. You don't have to use x. I happen to use x. You can use a random variable y, okay, or z, the vice versa. Or you can put this guy inside in the bracket. It's the same. Why? Sigma x cube is constant anyway. Whether you put that in the inside the expected value or outside of the expected value, is the same, right? Yes or no? Say yes. You've got to love to say yes. Okay, kurtosis. Kurtosis. This is kind of last parameters. Kurtosis, of course, in addition to all this, there is a mode, there is a median. We briefly discussed about it. Yeah, I hope you remember. Kurtosis is used, Greek notation, used as usual notation is kappa, K-A-P-P-A. That's what the people uses. It's called, is it correct? Pronounced as a kappa? K-A-P-P-A, kappa. And this is, of course, expected value of x. This is a capital letter, strictly speaking. X, 4th power. And the integration form is concerned, expected value minus infinity to infinity in general sense, or it could be start from the 0 to upper bound. And this is x, small x, minus mu x fourth power f xx dx. It can be positive or zero or negative. And as you look at, this is, people say, okay, measure of peakness. That's what I remember. Measure of peakness. What's good for it? I don't know. Really, that's the kind of answer I could say, because if this comes near zero, the value near zero, that's the situation. It has normal distribution. Zero is a normal distribution. Kurtosis come to close to zero. Then what's good for it? I have mixed feeling. And if this come up with a very peaky situation, then the value is supposed to be the positive, which has a really small, the standard deviation. Okay? And if it's below the normal situation, it's kind of the flatter. People claim it's supposed to be negative. But some people may use kurtosis to describe the characteristics of the model heavily, but I don't. I don't use much except the defining process. But when you develop into the statistical analysis, then you can compute and get some experience. Okay. Anybody involved on the project using probability theory, reliability theory? Okay. What's the reason to learn the reliability or structure reliability and probability? Because your advisor said, hey, go take a Professor Shin's course. No, I think you did a good thing. Because we are living in probabilistic model. It's reality. And you're all young, so you start young. When I was in Seoul National University, frankly speaking, we never had any probability course in the School of Engineering at that time. And our engineering division was located in Tennung. Still they have that huge buildings out there. Then it's away from liberal art. Liberal arts, math department belonged to liberal arts, and which is located at that time in Jongno Oga. I don't know, now I think they don't have it, right? They all moved to Kwanak campus there. No chance to learn that. Anyway, this is what the kurtosis, and kurtosis you can normalize it. If you want to normalize it, then what do you do? If you normalize it, then you simply divide this by some parameter. So this is x minus mu x fourth power, divide by the parameter fourth power, okay? That's what the non-dimensional kurtosis, simple the number. And I think that's about all for the parameter wise. And you are going to go through the item number 6 to item number 11. You remember? You have done it. This is due today, right? Next Monday. So over the weekend you can finish this up. Not spending more than an hour. 1 through 5, I'm pretty sure you reviewed it already. Covariance. Already implication is 2 parameters. So when we're looking into the correlation problem set today, then you will see the covariance come right into the picture. Okay, so covariance is describing the linear relation between the 2 parameters. And the definition first, let's look at the definition, is x random variable minus mu x, y random variable minus mu y. It's a variance. If you change capital Y to capital X, x random variable, then it's readily variance. Covariance, 2 random variables are involved, capital X and capital Y. So we'll leave as is. Then when we develop into the 2 variable correlation of the 2 variable, then you will see that. And of course, in the integration form, this is going to be, is it single or double integration? It's a double integration, minus infinity to infinity, then x mu x, y mu y, then f xy dx dy. 2 random variable double integration. Then as you look at the type of the integration to get the structure reliability is something like this. Just giving you the idea how difficult that is. Even bring the multi-dimensional optimization technique and takes a long time for computation-wise. Maybe a day? No. Maybe a week? No. Could it be a month? Still not sure. That's why I want to show you different approach, which is also popular. First order reliability method vice versa. So it's minus infinity to infinity, and you will end up solving like x1, x2, x3, all the way through xn. N could be 1 through dx1, dx2, so that's sort of the things what the structure reliability computation requires. I don't want to do that. I don't care how many multidimensional space you have to work. Simpler approach is better in engineering. I can live with the 5%, really 5%. Nowadays, less than 5% error, I can live with it. So no problems from there. So for the correlation, so that's a covariance, is a definite. How come it's still going up? How come it still goes up? I should really go straight this way. And as we'll drive soon, when you're dealing with the two parameters, two random variables, x, y, then you have to bring the correlation function or correlation coefficient, some relation between the two random variables, of course. Of course, if two random variables are independent, then you don't have to develop the relation between two. So to measure of correlation, I can introduce correlation coefficient or coefficient of correlation. Either way is the same. This is really measure of the degree of the relation. Degree of relation is a human relation, mathematical relation, is all close each other. Degree. Then if degree correlation coefficient is 1, then it's time to get married. Believe it or not, that's what's happening. Okay? In the human relation. So I can say rho xy is correlation coefficient is defined as sigma xy divided by sigma x and sigma y. So sigma xy is defined, is right here, is covariance sigma xy. So if I just rewrite here, this is going to be e to the x minus mu x, y minus mu y, and e to the sigma x minus mu x, e to the y minus mu y, and take a square root. That's what that is. If you look at carefully, mathematically, very straightforward. Not only straightforward, it makes sense. It makes really sense. Okay? And if, special case, if x and y are independent, assume this is a bachelor, x and y are independent, no relation yet. Without any mathematics, anything, Arlene, what's the rho value to be? Rho value. What's the rho x, y would be? No relation. Then rho x, y is equal to, without thinking anything. Okay? Yes, so you have no relation with the Jewish. So it's no relation. Rho is a measure of relation. 0. So this is equal to 0. Measure of the correlation is what rho xy is. So sigma xy, this guy has nothing to do with that guy. Okay, you can split into it. So if I write over here as a sigma xy, now this is independent situation between the x and y. Then of course you can have two sets, straight multiplications of this guy, which is minus infinity to infinity, x minus mu x, and fx x dx, and another one is y, is independent to each other, y minus mu y, and f y y dx, right? And one independent functional relation, another independent y only relations, and of course this is equal to the 0. You see, mathematically correct? Constant, right? If you take a two term, x times fx integration is mu x, right? Minus, this guy takes outside of integration, this guy, then it's simply integration of fx, which is equal to 1. So end up to have mu x minus mu x, which is equal to 0. 0 times 0 is 0. So mathematically good, but just a common sense, no relation. Measure of correlation is 0. So all fits into the human life. All the physics we are dealing in the lab is what God created. And problem number 6 through relation to number 11 is what you will do. Question? Clear. Yeah.
XY is the same joint probability density partial derivative of that?
Joint probability has a correlation, identical, same as rho same as this. That's what your question? In the joint probability, the rho xy, square root of the minus rho xy stuff is in there. Third term of normal distribution, joint normal, has rho xy identical. So you will see some action right now for the rho xy. Rho xy is a correlation, remember. Rho xy correlation. Bachelor, 0. Y is a function of x. It has a correlation between. Okay? Then the density function fxy should be the function of rho xy. The dependency has to be there. Questions? Okay. This red color doesn't erase well. Correlations function is not in your textbook or references. Advertisement. On the spring semester, I'm going to teach about the stochastic approach for structure, the system analysis. And that portion is more dynamics. This semester's is more statics version. So different sets of references, I'm using it for dynamic, stochastic dynamic problem. And this is a statics dynamic. And it's going to be nice pair. So if you have a chance, take that course. That's good. I try to teach easy way with capturing the physics of it. Okay, correlation function. Now, relation between x and y, which is two pair. The one pair could be sometimes xyz, xyz, another parameter can come into picture. So here, when you say relation, when you say the relation, something like this could be x variable, this could be the y variable. When you plot it, it could have a straight line up to the certain point. For example, x could be representing the deformation. So here, when you have a cantilever beam, then you apply the dynamic loading, a static loading. Okay, and this could be the x. So I could use did I say this is so I could use this is y. If I change the parameter as in the usual xy parameter is in different position, then it's confusing. Oh, this is supposed to be x-axis, this is supposed to be y-axis, right? You don't have that feel? Because x and y is already prescribed in your heart. X must be horizontal axis. Y is supposed to be the vertical axis. You just prescribed here, right here. It doesn't have to. So innovation, back into innovation. Steve Jobs, very different person. He doesn't want to just walk with all other guys in comfortable and really flat, wide, straight highway. He wants to explore something else in the sidewalk. He just doesn't like XY prescribed as horizontal and vertical. That's what his nature seems to be. I bought a book last year. The book, I forgot. The book written by Steve Jobs. Not directly. Other guy really wrote it after he really talked with Steve quite long time. Then he generate innovative idea. What's innovative idea Steve did? iPhone. Right? iPhone. Do they have the button, alphabet button? Don't have it. Until I feel before iPhone came out, all the phone has a push button. Any phone has a push button. This iPhone don't have a push button. Why? In our heart, we have a fixed set of the mind at the one corner of the heart, saying that to use alphabet, you need the push button. You need a button. No question asked. You need a button. That's what happened. He doesn't want to have a button. So he just uses just to tap it. Then the button pattern comes right out. And never used fingers before. It's not 10 years ago. It's a couple of years ago, 2 to 3 years ago, before iPhone came out. Everybody uses different approach, which is very tedious. But since iPhone came out, everything is a finger. 2 finger, only 1 finger. That's the innovation. So, like you with a beautiful brain, should be able to generate innovative idea in the reliability theory and structural reliability theory. Integration approach, a lot more simple way. There are few people work hard on the structure reliability. They all retired at least 5 to 10 years ago. They sacrificed themselves to bring up the knowledge up to today's era. Without them, it would be hard, but I feel this is really time to jump the next step. Not the iterative way. I'm not talking about, oh, you have to know this to get that from here to here, you have to go through that curve. You have to follow the curve. That wasn't the Steve Jobs idea. You can jump from here to here. That's what I want to see is happening in ocean systems engineering. Got it? That's what you should think. This is all chansori, you know. Arlene, you know what the chansori means? It's all the nuisance stuff. So, but it's a nice chansori. Yeah. Remember chansori, Arlene, that's it's a nuisance stuff. Okay, I'm going to say this y is loading and x is a deformation, okay? But usually what we always do is like this. That is comfortable, including myself. Y is a deformation, x is the loading. And assume the straight line. Straight line is good up to the certain point. Up to the certain point, x is like up to, let's say, 100 kilograms. Okay? Then I could say, oh, then corresponding y could be up to 1 centimeter, for example. Okay? That's what range, linear elastic range. Some of you didn't take the mechanics. Who was it? I think it made different measure. Whatever. So up to here is like when you plot it, up to here is something like a linear. After that usually it's getting into nonlinear. God bless you. Okay. Could go this way, nonlinear regime, or inelastic regime. When you unload the load, then it may not go back to the zero here, because permanent deformation could be set. So if you don't have the line, but if you're dealing with only for up to here, then it's perfect. The linear relationship between x and y is a perfect linear. This is one typical phenomena in reality. And life is not just linear. Always there is uncertainty coming to picture. So another situation could be this in your notes. Could have some spread in reality, not a straight line. This is if I just somehow fit a straight line here, it's somewhat linear. So this is somewhat linear relations. So this is a perfectly linear, very much predictable. Rho xy is perfect, none. In this case, well, I have to fit the straight line, so-called regression line. Best to fit. If it's a curve, the regression curve, like a polynomial, straight line approximation. If this uncertainty width is small, this regression line is very good, and this is like a least square. As you may know, least square approach. Get the deviation between the measured and predicted and minimize it. We're going to do that quickly. And some are really nonlinear. Some behavior is nonlinear. Some take the data, then nonlinear, not the linear, predictable. This is very much analytical relation. But it's not nonlinear. Nonlinear, you are taking some courses on nonlinear FEM analysis. Nonlinear behavior is quite different sometimes. Okay, a lot of material falling into that category. Other types are totally chaotic. What does it mean, totally chaotic? It's just unpredictable. Unpredictable. You should avoid to have a date with such an unpredictable 남친 or 여친. That's a disaster pattern. No correlation. The way he behaved yesterday is quite different from the behavior that he has today. You're supposed to say goodbye. Yes or okay. And 여친, same thing. So no correlation. Some has a good correlation. Rho xy are good, consistent, then you can develop the probability model for the person you are dating, then work with it. Okay? So this is what those situations is. Okay, I'm going to stop here, and we'll continue next week. And probability model that you will get it today, I just wrote for 6 probability model, which is somewhat popular. Among such a model, the log normal, sometimes people write like this, or sometimes simply log normal, sometimes they delete this as a 1. Doesn't make any difference. This is a very nice probability model, which you can introduce the skewness in the systems and kurtosis and all that. And when I assigned the problem in the last page, I said include the log normal probability model plus 2 additional model. That doesn't mean that 2 additional out of 6, no. Any the probability model you may work out now or interested or look for the literatures and generate your own model using your imagination and the desire. I don't want to fit you in the alley that I want to just go through. No, I want to really see what pattern you're going to really go. I want to really see your personality as a parameter, mean, standard deviations, skewness, kurtosis, and all that. That way, I feel you can have more room to maneuvers and vice versa. I'm pretty sure the way I dealing with the assignment is quite different from other people. But that's what I want to go and follow the directions and try. Okay? Okay, have a nice weekend. I'll see you Monday.